Welcome to our YouTube channel. Today we'll be diving into some technical questions about Node.js, AWS, and more. Let's get started. Question: if Node.js asynchronous is used but no queues are used, would it become event-driven? Node.js is inherently event-driven, even without explicit queues. This is due to its core design, event loop. Node.js employs a single-threaded event loop that continuously monitors for events. When an event occurs, like a network request, file I/O, or timer expiration, it's registered with the event loop. The event loop efficiently manages these events, executing callbacks associated with them when appropriate. Asynchronous operations boss Node.js leverages non-blocking I/O operations, allowing it to handle multiple tasks concurrently without blocking the main thread. When an asynchronous operation is initiated, it's delegated to the underlying OS, and the event loop is notified when the operation completes. This notification triggers the execution of the associated callback function. Key points: no explicit queues. While Node.js doesn't rely on explicit queues like traditional message queues, the event loop implicitly manages a queue of events and their corresponding callbacks. Event-driven paradigm. The event-driven nature of Node.js allows it to efficiently handle a large number of concurrent connections and requests. Single-threaded efficiency. The single-threaded model combined with the event loop enables Node.js to achieve high performance and scalability. In conclusion, Node.js' event-driven architecture is fundamental to its asynchronous programming model. Even without explicit queues, the event loop and asynchronous operations work together to create a highly efficient and scalable environment. Question: does Node.js have retries built in because of its implicit event loop? Node.js doesn't have built-in retries specifically tied to its event loop. However, it provides the tools and environment to implement retry mechanisms effectively. Asynchronous operations and callbacks. Node.js' asynchronous nature allows you to define callback functions that are executed upon the completion, whether success or failure, of an operation. This enables you to create a retry loop within your callback function, where you can reattempt the operation on failure. Event loop for efficient scheduling. The event loop ensures that your retry attempts are scheduled and executed efficiently without blocking the main thread. It manages the timing and order of retries, allowing for strategies like exponential backoff. Third-party libraries. Many third-party libraries provide convenient retry mechanisms tailored to specific scenarios, such as Retry, a popular library offering flexible retry strategies and error handling. Axios Retry, a plugin for the Axios HTTP client that simplifies retrying failed requests. Custom implementation. You can implement your own retry logic using Node.js' S-core modules and asynchronous programming techniques. This allows for granular control over retry behavior, including number of retries, retry intervals, error handling, custom retry conditions. While the event loop itself doesn't directly handle retries, it provides the foundation for implementing robust retry strategies in Node.js applications. By leveraging the asynchronous nature of Node.js and the efficient scheduling provided by the event loop, you can create reliable and resilient applications that can gracefully handle transient failures. Question: Bedrock, LangChain, Rag, ChatGPT, ILM, VectorDB. What roles do they play in a Rag chatbot? In a retrieval-augmented generation Rag chatbot, these components play distinct roles. 1. Bedrock, foundation model provider. Bedrock provides access to a variety of foundation models, including large language models like Jurassic 2 Jumbo. Custom model training. It enables users to fine-tune these foundation models on specific datasets to create custom models tailored to particular tasks or domains. 2. LangChain, orchestration framework. LangChain acts as the orchestrator, managing the flow of information between the various components. Prompt engineering. It helps in crafting effective prompts to guide the large language model's responses. Chain creation. It allows for the creation of complex chains of prompts and responses, enabling more sophisticated interactions. 3. RAG or retrieval augmentation. RAG is a technique that leverages a vector database to retrieve relevant information from a knowledge base. Contextual response. By incorporating this retrieved context, the large language model can generate more accurate and informative responses. 4. ChatGPT language model. ChatGPT is a powerful large language model capable of generating human-quality text, translating languages, writing different kinds of creative content, and answering your questions in an informative way. Response generation. In a RAG chatbot, ChatGPT is often used to generate the final response, incorporating the retrieved context from the vector database. 5. Vector database, knowledge storage. The vector database stores embeddings of documents or text chunks. Similarity search. It enables efficient similarity search, allowing the retrieval of the most relevant information based on a query. Contextual retrieval. By comparing the query's embedding to the embeddings in the database, it helps identify the most pertinent context for the large language model to consider. In summary, Bedrock provides the foundational models. LangChain orchestrates the process. RAG leverages the vector database to retrieve relevant information. ChatGPT generates the final response. Vector database stores and retrieves the necessary context. By working together, these components enable the RAG chatbot to access and process information from a vast knowledge base, resulting in more informative and contextually relevant responses. Is AWS serverless architecture auto-scaled automatically? Well, yes. AWS serverless architecture, particularly AWS Lambda, is designed to auto-scale automatically. This means that your functions can handle varying levels of traffic without requiring manual intervention. Here's how it works. Automatic scaling. When your Lambda function receives a request, AWS automatically scales the number of instances to handle the load. If the load increases, more instances are provisioned to process the requests concurrently. Conversely, if the load decreases, idle instances are terminated to optimize resource utilization. Concurrency limits. You can set concurrency limits to control the maximum number of concurrent executions of your function. This helps prevent overwhelming your function and ensures a smooth scaling experience. Provisioned concurrency. For predictable workloads, you can provision a specific number of concurrent executions in advance. This guarantees that your function can handle a certain level of traffic, even during peak times. By leveraging these auto-scaling capabilities, you can build highly scalable and cost-effective serverless applications without worrying about managing infrastructure. In AWS, if you have auto-scaling, is it considered high availability? Well, yes, AWS auto-scaling can contribute to high availability, but it's not the sole factor. While auto-scaling is a powerful tool for ensuring your application can handle varying loads, it primarily focuses on scalability. To achieve true high availability, you need to consider a combination of factors. Key factors for high availability: redundancy, multiple availability zones, or AZs. Distributing your resources across multiple AZs can protect against failures within a single AZ. Redundant components. Having redundant components like load balancers, databases, and network devices can help mitigate single points of failure. Fault tolerance. Designing your application to gracefully handle failures and recover quickly. Implementing robust error handling and retry mechanisms. Load balancing. Distributing incoming traffic across multiple instances to prevent overload. Using load balancers like elastic load balancing to ensure even distribution of traffic. Auto-scaling, automatically adjusting the number of instances to handle varying workloads. Preventing performance degradation and ensuring optimal resource utilization. Incorporating auto-scaling into a high availability strategy. Auto-scaling can enhance high availability by rapid scaling, quickly adding or removing instances to accommodate sudden traffic spikes or drops. Fault tolerance, automatically replacing failed instances with new ones. Cost optimization, scaling resources up or down based on demand to reduce costs. However, it's essential to combine auto-scaling with other strategies to achieve comprehensive high availability. By carefully designing your architecture and implementing robust redundancy and fault tolerance mechanisms, you can build highly available and resilient applications on AWS. What is an AWS availability zone? An availability zone, or AZ, is a discrete data center with redundant power, networking, and connectivity located in a specific geographical region. Each AZ is physically separated from other AZs within the same region, providing isolation and protection against failures. Key characteristics of availability zones: physical separation. AZs are located in different facilities, reducing the risk of correlated failures. Independent infrastructure. Each AZ has its own power, cooling, and networking systems. Low latency connectivity. AZs within a region are connected with low latency, high bandwidth networks. Fault isolation. If one AZ experiences an outage, the other AZs within the region can continue to operate normally. Why are availability zones important? High availability. By distributing your applications and data across multiple AZs, you can significantly improve the availability and resilience of your systems. Disaster recovery, AZs, enable you to implement disaster recovery strategies by replicating data and applications to different AZs. Scalability. You can easily scale your applications by launching instances in multiple AZs. Compliance. Some compliance standards require data to be stored in specific geographic regions. AZs allow you to meet these requirements while maintaining high availability. How to use availability zones. Multi-AZ deployments. Deploy your applications across multiple AZs to increase fault tolerance. Database replication. Replicate your databases across multiple AZs to ensure data durability and availability. Load balancing. Distribute traffic across multiple AZs to improve performance and reliability. Disaster recovery planning. Design a disaster recovery plan that leverages multiple AZs to recover from failures. By understanding and utilizing availability zones, you can build highly available, fault-tolerant, and scalable applications on AWS. AWS managed versus unmanaged services with examples for each. AWS managed services. Managed services are cloud services that are fully managed by AWS. This means that AWS handles the underlying infrastructure, security, and operations, allowing you to focus on your application development. Examples of AWS managed services: AWS Lambda, a serverless compute service that allows you to run code without provisioning or managing servers. Amazon DynamoDB, a fully managed NoSQL database service that provides fast and predictable performance. Amazon S3, a highly scalable object storage service that can store and retrieve any amount of data at any time from anywhere on the web. Amazon RDS, a managed relational database service that makes it easy to set up, operate, and scale a relational database in the cloud. Amazon Elasticache, a managed in-memory data store service that delivers fast performance and reduced latency for your applications. AWS Unmanaged Services. Unmanaged services require more hands-on management. You are responsible for configuring, managing, and maintaining the underlying infrastructure. Examples of AWS unmanaged services: Amazon EC2, a web service that provides secure, resizable compute capacity in the cloud. You are responsible for managing the instances, including patching, security, and scaling. Amazon VPC, a service that lets you define a logically isolated section of the AWS cloud where you can launch AWS resources in a virtual network dedicated to your account. You are responsible for configuring the network, security groups, and routing tables. Amazon EKS, a managed Kubernetes service that simplifies running Kubernetes on AWS. While AWS manages the control plane, you are still responsible for managing the worker nodes and applications. Key differences: feature managed services, unmanaged services. Infrastructure management: AWS, you scaling automatic manual or automated security. AWS, you patching. AWS, you cost higher upfront costs, lower operational costs, lower upfront costs, higher operational costs. Focus application development, infrastructure management, and application development. By understanding the differences between managed and unmanaged services, you can choose the right services for your specific needs and workload. In AWS, is multi-AZ deployment active, or passive? AWS multi-AZ deployments are typically configured as active-passive. In an active-passive configuration, one instance, the primary, handles all the traffic, while the other instance, the standby, remains idle. If the primary instance fails, the standby instance automatically takes over and becomes the primary. However, it's important to note that the specific configuration can vary depending on the service and your specific requirements. For example, Amazon RDS multi-AZ deployments in RDS can be configured as active-passive or active-active, depending on the database engine and your needs. Elastic load balancing. You can configure load balancers to distribute traffic across multiple availability zones, effectively creating an active-active configuration. Ultimately, the choice between active-active and active-passive depends on your specific needs, such as performance. Active-active configurations can provide higher performance and scalability by distributing the load across multiple instances. Reliability. Active-passive configurations can provide higher reliability by having a standby instance ready to take over in case of a failure. Cost. Active-active configurations may incur higher costs due to the need to run multiple instances simultaneously.